Hello everyone, this is Dr. Lennon, and we're going to start talking about power series and polynomials, Taylor polynomials explicitly. So what these are a way we've investigated series, and now we're going to look at series of polynomials essentially. So polynomials are really nice functions. They have, they're differentiable, they're continuous, really nice curves. So one of the things that was figured out was how to use polynomials to help approximate more complicated functions. And so that's kind of what the idea of Taylor polynomials are. And with really nice functions, some functions have infinitely many derivatives, and that's when you can create Taylor series where you use infinite polynomials as representations of functions. So that's what we'll be looking at. The Taylor polynomials today, so just the finite ones. So let's jump right in. So let f be a function with, let's say its first n derivatives, f prime, f double prime, all the way up to the nth derivative defined at some point a, which will be the center of our Taylor polynomial at a, or at x equals a. So the nth order Taylor polynomial for f with its center defined, or with its center at a denoted, excuse me. So we're going to call it P of n, kind of similar to how we used S sub n for partial sums. Has the property that it matches f in value, slope, and all derivatives up to the nth derivative at a. So this is what we're defining. So that is basically this Pn of a is found, so it equals f of a when you plug it in. And also, if you look at P prime of n at a, it equals f prime at a. And this is true all the way until you get to the nth derivative. So you've got agreement at all of these values. So Pn taking the nth derivative at a is the same thing as when you take the nth derivative of the actual function and plug in a. Okay, so the nth order Taylor polynomial is, or centered at a, is, so how do we find it? Well, basically, we just take a bunch of derivatives and plug those things in and find each one. So it's f of a plus f prime of a times x minus a plus the second derivative plugged in a over 2 factorial times x minus a squared, and then you go all the way up until you get to the nth derivative. So the nth derivative plugged in at a over n factorial times x minus a to the n. So those are the instructions for how to actually construct this thing, and in terms of series notation, that just looks like the series from k equals 1 to n of ck times x minus a to the k, where your ck is just given by the kth derivative at a over k factorial. Okay, so that's a lot, but the basic pattern, once you get the hang of it, it's not too hard to write down the Taylor polynomials for a lot of these things, and once you work with series, you'll have quite a few memorized. So, example, let's go ahead and do one. So, find the general Taylor poly P sub n at a equals 0 for f of x equals the sine of x. So basically, the first thing we want to do is try and write down what the derivatives look like plugged in here. And one thing about sine of x is the derivatives repeat after a while. So we start with sine of x. The first derivative is cosine of x. The second derivative is then going to be minus sine of x. The third derivative is going to be minus cosine of x. And then once you do the fourth derivative, you get back to sine of x. So what we really want to use these derivatives for, and then that just keeps continuing. What we really want to use these in is to figure out the coefficients. So we want to plug in 0 into each one of these things. So we know the sine of 0 is 0. We know the cosine of 0 is, in fact, 1. We know, so the second derivative at 0, we have a cosine again, so that's going to be 0. Sorry, sine again, so that's going to be 0. Then the third derivative, cosine pops back in, but this time it has a negative in front, so we get negative 1. And then we come back to something with a sine in it, so that goes to 0 as well. And this pattern continues. So you can see basically all of your even derivatives are 0, and each of the coefficients produced from the odd derivatives are either plus or minus 1. So what does this look like when we make the polynomial? Well, normally you have to do x minus a to the power, but in this case, a is equal to 0, so they're just going to be powers of x. So our p sub n of x, we can just kind of write out the terms. So we start off with 0, then we're going to have x, and then we get a minus. So this third one, this is going to be x to the third power, and then remember we divide by that same power factorial, and then it's going to alternate. Then we're going to get an x to the fifth over 5 factorial. Then we'd get minus x to the 7th over 7 factorial, then plus x to the 9th over 9 factorial, and so on until you get to your general term, which is going to look like, let's see, so we're going to need our general term, we know it's just going to be, so it's going to be a little bit tricky here, just because we need a negative 1 to some power, and then we need an x, and then we need some factorial. So what's going to happen? Well, this is happening at index 1, and this is happening at index 3. So if you double it, and then, so we need it to alternate there. So let's look at the indices. Let's look at the indices to help guide us. This is index 1, this is index 3, this is index 5, this is index 7. So basically what's going on, this is So if we want to make indices for these, so say we call this n, and we start with, I don't know, 0, 1, 2, 3, 4. To get the power, you can see that's all we're doing it is we're doubling it. So x is going to be raised to the 2n plus 1. So then the bottom is going to be the 2n plus 1 factorial. And then we can just use -1 to the n because we're even, odd, so -1 to the n. So that would take care of our general term. So that would be the, so I don't know, let's say this is the power, and then this is the index we want to use. That's kind of how I think about it and break it down in my head to line those things up to create the general term, but other people probably do it different ways as well. So a good one for you to try. So practice, and it's going to be very similar. Write the general Taylor polynomial for y equals cosine of x centered at a equals 0. And it's going to be very similar. You might even guess it based on the series that you see for sine here. Let's do another one. Another famous Taylor polynomial that comes up quite a bit is the one for e to the x. So let's go ahead and do that one. So write the Taylor polynomial for y equals e to the x centered at x equals 0. All right, a equals 0. I keep writing x. Book is using a there. When these things are centered at 0, I believe, in fact, they're actually technically called Maclaurin polynomials. So Maclaurin wrote the ones where they were just general at a equals 0, and then Taylor generalized it so that they could be written at any index by just using that slight difference on the coefficients and then kind of translating the x part. Okay, so again, what we want to do is just take a bunch of derivatives here. So maybe I should be using x, I'm just using y this time. But we have y as e to the x. And then this is actually pretty easy because we know when we take the derivative, we just always get e to the x. And then e to the 0 is always going to be 1. So y of 0 is 1. Y prime of 0 is 1. Y double prime of 0 is 1, and so on. So we can write the Taylor polynomial pretty quickly. So Pn of x here is just going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and your general term is just going to be x to the n over n factorial. So that would be your Taylor polynomial for e to the x. Very regular indeed. So that's pretty straightforward. So let's talk about the let's go ahead and stop there, and we will continue next time talking about power series in general, which we're already kind of touching on, and then we'll write down, in fact, what Taylor series are for these things, and we'll look at how we can use tools of calculus to help do some things like differentiate them, integrate them, and use them to solve some other problems. So this is Dr. Lennon signing off.